All right, folks. This is Kevin Franke. We're going to go ahead and get started. It's 11 here in Mountain Time. And I just want to thank you for your attendance and participation in this webinar. We hope it will be useful to you. I am an assistant professor at Brigham Young University in Provo, Utah, and I'm joined by my colleague and good friend, Dimitrios Zekkos, who's an associate professor at the University of Michigan. And both of us have been pursuing research applications for unmanned aerial vehicles in geotechnical engineering. And this webinar is specifically focused on post-disaster reconnaissance. We want to acknowledge and thank GEAR for allowing us to give this webinar and inviting us, as well as the National Science Foundation for its continued funding for this research, and the Center for Unmanned Aircraft Systems, which also provides funding for us to be able to pursue this research. So just by way of an outline, we hope to cover all of these topics today, and I realize that these are a lot of topics to cover in a 1-hour time frame, but we'll definitely do our best. I want to point out that we are recording this webinar, so if any of you would like to go back and rewatch any aspect of it, that should be available on the GEAR website within the next couple of days. So what I'd like to do is go ahead and jump right into various types of platforms that we use as engineers and scientists today. The different types of platforms that are commonly seen in different applications, we can boil it down to just a couple of general generic types. I do want to point out before I get into these different types that there are many, many different types of small UAVs, and creators and designers of these platforms almost have limitless capability to put tweaks on their designs and to do new things. And so it's really remarkable what they're able to do. And so when I speak of types of UAVs, I'm not referring to any specific brand or specific platform, but I'm referring to just general classifications of UAVs. So the first general classification is what I would call a fixed wing platform. So these are the more traditional, like what you might think of as a remote control airplane, though they're looking a lot more sophisticated. And different types of these platforms are manufactured by companies like Trimble, SenseFly, 3DR, or like we do in our research group, we often just customize and build our own for our own specific research needs. The next type of platform is very popular today, and when you hear about UAVs or drones and applications, both commercial and hobbyist, they tend to be multi-rotor platforms. So these are platforms that have more than one rotor, typically 4 or more, and these platforms are great for a variety of reasons. They also tend to be a lot more affordable than the fixed wing platforms. And so different manufacturers, every manufacturer makes a multi-rotor version, but some of the more popular ones are developed by DJI. SenseFly is also developing some new and exciting multi-rotors. The third general type of platform is a single rotor platform. So this is like a miniature remote control helicopter. And so it may not appear as exciting as a multi-rotor, but it has some interesting capabilities that multi-rotors don't necessarily have. And it has some strengths that make it very useful for applications in the field, particularly in challenging environments. So these are the general types of UAV platforms. If I was to summarize pros and cons of the different types of platforms based on our experience, I could summarize it like this. Referring to fixed wing platforms, some of the positives regarding those platforms, they tend to be very stable in wind. We've flown these platforms in 40 to 50 mile per hour winds, and they do pretty well. They have generally low vibrations, and so we can get some very clear imagery from them. And they can carry very large payloads depending on the wingspan or the size of these platforms. Also, because they tend to be pretty efficient in flight, they tend to have longer flight endurance, and it's not unheard of to see just from a simple battery-powered platform, flight endurance is on the order of an hour to 2 hours for a single flight. Thanks for joining. If you guys just joined, I kindly ask you to please mute your microphones. We're getting a lot of feedback on the webinar. If everybody could please mute their microphones, that would be great. A couple of the cons against fixed-wing platforms, however, is that they can be very hard for amateur pilots to fly. They tend to require a lot of practice. And they can require a lot of landing space, though some of the newer platforms or more expensive fixed-wing platforms are offering the capability of landing on a dime, which is pretty remarkable. They can have some difficulty imaging vertical objects because they tend to point their sensors straight down or at a very steep angle. And they can have difficulty navigating in cluttered terrain because they fly at such high velocities, and they don't have the ability to hover, though that may change in the near future with platforms like tail sitters. Looking at the pros and cons of multi-rotor platforms, these platforms tend to be the most stable in flight, assuming that there's no wind, and they can carry reasonable payloads, usually up to about 7 to 10 pounds if you're flying a large multi-rotor. And they have superior maneuverability, and they require very little space for takeoff and landing. The downside to a multi-rotor platform is they tend to be pretty unstable in winds. When we've tried to fly them in winds around in excess of 20 miles per hour, we've had some scary moments. And they can also have some pretty short flight endurances, usually between 10 to 15 minutes per battery if you're carrying a sensor. They can go up to 25 or 30 minutes if you're not carrying a sensor. And we've also had some issues with these platforms being susceptible to extreme temperatures. Welcome, folks. If you just joined the webinar, we're glad you're here. If you would be so kind as to please mute your microphones, that would be great. We're getting a lot of feedback from you. The final platform are the single rotor platforms. The pros for these is that they have pretty much the same maneuverability as a multi-rotor platform, but they tend to be much more stable in windy environments due to their higher polar moment of inertia, and they tend to also perform better in extreme temperature environments. Some of the downsides, though, is that they can be a little more difficult to fly and operate, and they tend to have more vibrations than multi-rotor platforms. And if you start dealing with some of the larger single rotor platforms, they can pose a life safety hazard, and so you want to be sure not to operate them over large crowds, where if it's going to come down, they may actually really hurt somebody. So again, if you just joined the webinar, thank you for joining. If you would please be so kind as to mute your microphones, that would be appreciated. We can hear your feedback, and it tends to disrupt the presentation. So at this time, I'd like to turn the time over to my colleague, Dimitrios Zekkos, and he'll talk a little bit about different types of UAV sensors.
Well, thanks, Kevin. Everybody can hear me, I guess?
Yes.
Okay. Kevin, next slide, please. So we'd like to talk a little bit about the sensors we put on the UAVs. First of all, I should mention that there are a number of sensors that are used in different types of drones for communication, flight control, and more recently, collision avoidance. And there are a lot of new sensors coming up for those also all the time. We're not going to focus on those in this presentation. And in terms of field reconnaissance data acquisition, which is the focus in this webinar, by far the most common are vision-based sensors, essentially cameras. And so with cameras, you can collect pictures or video. You generally want to have a relatively high-resolution camera, and so pictures of at least 12 megapixels are needed, or higher than that. And the video can vary also. More recently, many of these drones have a 4K ultra-high-definition video, which is essentially a high-resolution video frame with better color attributes and has also high frame rate. which is important for our purposes. The processing this type of data can actually generate very good information for geotechnical reconnaissance, and we hope to communicate that with Kevin today. Before we show you anything else, I think it's important to mention that in order to collect quality imagery data, there are a number of considerations. The three probably the most important ones is weather, and especially sunlight, and the position of sun between the sun with respect to the drone and the target that you're trying to collect data for. The viewpoint of the UAV, you have to be able to see from the UAV what you're trying to map. Without that, you won't be able to map where your target. And finally, pixel density. Pixel density is key for feature recognition. If you don't have a high density pixel density photo, you will not be able to identify the features that you're looking for. And that is not affected only by the camera, which of course is very, very important, but also from your flight characteristics, especially how close to the target you're flying. Overall, the better the camera and the closer to the target you fly, the better data you should be able to get. Next slide. Now, one of the things that Kevin and I think are very, very important about the UAVs, and the reason we're doing this is because UAVs provide you with the mobility and accessibility that other approaches, such as land-based surveys, but also satellites, cannot provide. I think this is nicely communicated by this example, the example of the November 17th magnitude 6.4 Lefkada earthquake. We were able to deploy in that area just 2 days after the earthquake, and there were a number of a large area that was heavily damaged by landslides, and there were kilometers of coastline that were completely inaccessible by land, and we were able to fly the drone and reach those areas. And as you know, through your affiliation with GEAR, our major focus is on collecting perishable data, and we want to be there as soon as possible before things change. The next picture, if Kevin, if you can click. Yeah, this is the same site 5 months later, so not that much later, but so 5 months later, and it's the exact same site. If you click again, Kevin, you'll be able to see that already within 5 months, a significant amount of debris material has been washed away by the sea. And of course, if you were to visit now the area, you'll get maybe different conclusions. For example, if you're trying to estimate volumes, landslide volumes, you will probably get a different answer than if you do it 5 months later than if you do it 2 days later. So the drones allow you for this mobility and accessibility of sites. And so that's one of the key attributes. The next slide highlights the other attribute that's very, very important for UAVs is viewpoint. Because you can fly the drone in different directions, you can actually get a side view, a front view, or a plan view of a target. And Kevin, if you click, maybe you can see this is the exact same target. You can probably see this structure there with that it was damaged within the landslides, and you're essentially looking at the same feature from different viewpoints. That's something that is many times very difficult to do from the land, and also impossible to do with satellites, because from satellites you typically look from the top. And so I think this perspective can be really valuable in terms of understanding what is going on in this case with the landslides. Next slide. Beyond the cameras, there are a number of other sensors that are being used. I will start with LiDAR. You probably know of LiDAR. We've been using it extensively with GEAR. It's essentially a laser that allows you to collect a 3D point cloud of the 3D point cloud of your target, and essentially get a very high resolution geometry of whatever your target is. And LiDAR has been mounted on drones. We've done it too, and you can collect this information from a drone. it's very valuable for geometry, and we'll see that you can get similar type of information also nowadays with cameras. Beyond though the visible, the cameras, there are also other frequencies that we typically don't use that often that also can provide useful information. To the right, there is an image of the electromagnetic spectrum, and you can see that a regular camera will be looking at a specific range of frequencies or wavelengths that are visible, the red, green, blue, RGB, and these are specific wavelengths, and that's the ones we can see. However, there are other wavelengths, other frequencies that we can actually also collect data, and there are cameras that actually can collect this information. So, for example, infrared collects longer wavelengths, a little bit longer wavelengths waves, electromagnetic waves that you can help you detect body heat, essentially, can be used for inspections, for resource management, for surveillance, search and rescue. And so this actually is very valuable to us. Alternatively, you could use also a thermal camera for something like that. Near infrared, which is actually between visible frequencies and infrared, is very good for assessing health of vegetation. And if you have a near infrared camera along with a visible camera, you can get a lot of information about the ground and see below actually vegetation. There are also multispectral cameras that are essentially combination of other cameras. You can combine, for example, the visible wavelengths with near infrared and infrared, and you can collect, by fusing this data, you can collect much more information about your target. The next slide. Next.
Okay, so I have to talk a little bit about current UAV regulations, particularly here in the United States. I can summarize it by basically saying that it's messy. It's very difficult to fly commercially or for research legally here in the United States currently. The problem was a lot worse 2 years ago because it required that you receive a full certificate of authorization and that you have a licensed pilot operate your UAVs, and all of your UAVs had to be safety certified. And so these requirements limited very much who could perform commercial or research operations with UAVs. FAA improved things a little bit with what's called the Section 333 exemption, which was essentially intended to expedite the commercial practice of UAVs in the U.S., and it has helped, but it's still holding us back. And one of the problems is that the petition process with the FAA has literally become log-jammed, and if you submit a Section 333 exemption proposal, it can require several months before the FAA even looks at your application. So changes are fortunately coming in the United States, however. The United States Congress has mandated that the FAA develop a practical and a useful set of rules that will allow the safe commercial operation of drones here in the United States. And a draft set of these regulations has indeed been developed, and I encourage you guys to go check them out. I've included a link here that you can follow on your own time, and it will summarize. But in general, if I were to summarize it, I would say your UAV will simply need to be registered, and that's just a simple online process and a fee of $25 to $50. You need to demonstrate that you have a licensed operator, but understand that this isn't the same as a pilot's license. This license is given just by your pilot taking an online test to prove that they're capable and know the safety regulations associated with UAVs. You need to stay below a maximum altitude of 500 feet above the ground surface, and you need to stay away from large groups of people, unless you have a special exemption which the FAA can grant based on your operator's qualifications and training. And then you also need to only operate your UAVs in the daytime and only in Class G airspace. Class G basically means you're not going to go near critical structures or near airports. As far as international regulations go, there is no standard. It varies from country to country. And so depending on where events occur throughout the world, it can be quite an exercise to obtain authorizations to fly UAVs. Currently, we're working with Japanese authorities to try to obtain permission to fly over Kumamoto. Interestingly enough, Ecuador doesn't appear to have any regulation or requirements. Oh, folks who just joined, if you would mind please muting your microphones, that would be great.
Okay, thank you.
Sure. Now, as far as getting permissions to run UAVs internationally, you need to consider this on a case-by-case basis. And this would be one of the first recommendations that I would formally like to make to GEAR, that GEAR perform some preliminary, what I call homework, and identify some countries where they feel like some disasters are likely to occur in the next few years, and try to reach out and get much of this authorization done beforehand so that when a disaster does occur, we can expedite that process and obtain the necessary authorizations in a timely manner. So now what we'd like to do is shift gears and focus a little bit on some of the potential uses for UAV-based data. I'll start by just sharing the obvious, that we can get some aerial imagery and video of sites of interest. Sometimes when you're on the ground at some of these damage or disaster sites, it can be difficult to wrap your arms around what's happening. For example, in this first picture A, that's me standing on the port of Iquique in Chile in 2014, and the port was absolutely devastated by liquefaction. And when you're on the ground and the cracks and the damage is that big, it can be difficult to understand what's going on. But in the picture below that, labeled B, that is an image from above, from our UAV, just a DJI quad rotor and a GoPro camera. And when you get above the damage and look at it from a larger perspective, oftentimes it's easier to see what's going on, and crack patterns and damage patterns become a little more evident. Another thing that we can get from these, another type of data we can get, are orthorectified images and digital elevation models. Now, for those who don't know what an orthophoto or an orthorectified image is, you could imagine that if we were looking down from above on two different buildings, and you can see, hopefully everyone can see these animations. We have a larger building on a lower plane and a smaller building on a higher plane. If we were looking at this from above, from a single point as a UAV, this perspective view is what it would look like in the photograph. However, that's not necessarily what we want to analyze or evaluate to be able to get some objective change detection or displacement measurements. And so we want to rectify everything to a standardized plane, which is what we get in this orthographic view. So with these models that we develop from the digital imagery, we can create a variety of different models. We'll talk about 3D point cloud models here shortly, but we can also obtain, as you can see in the bottom left, an ortho projection photo. And from those, we can import them into any standard geographic information system like ArcGIS and develop digital elevation models and perform some change detection or try to measure deformations that way. Now, the development of 3D models or 3D point cloud models is an exciting advancement that has been happening over the last several years in photogrammetry. And to give you some background how this works, we like to use the process called structure from motion. And to help you understand what structure from motion is, here's a nice little demonstration. Everybody should know what this structure is. This is the famous Sydney Opera House. And if you look at the Sydney Opera House, or if you go online and Google the Sydney Opera House, you're going to get pictures from about every possible angle of this famous structure. And as a human being, as we look at this structure, we tend to be able to see that there's distinct features on this structure that stand out and make it recognizable to us. For instance, these points or these tips of these horned ceilings are very unique to this structure, and we don't find them on very many structures throughout the world. The way structure from motion works is, imagine the computer algorithm being able to look at two different sets of images and recognize that this point and this point represent the exact same object. Likewise, we could look at two other points that represent the same object and a whole different variety of different points that can represent the same object. Now, the idea is that this algorithm can back calculate, recognizing these same objects or similar objects in different photographs. We can back calculate the third dimension and calculate where the location of the camera was in 3D space relative to the object that's being photographed. And so once we have that third dimension, well, now we have the ability to create 3D point cloud models. So using digital imagery capture from our UAVs, we can create 3D models of different damage sites. For instance, this top figure is from the liquefaction damaged pier in Iquique, Chile, from the earthquake in April in 2014. And from the same earthquake, down below you can see on the left an actual photograph of a bridge where liquefaction occurred. And then on the right, the 3D meshed or textured model that was developed after structure from motion computer vision was performed. And the value of these models now is that we can go in and we can make measurements in these 3D models and capture details that we may not have had time to capture while we were there in the field. So we can be a lot more deliberate, a lot more careful with the details of our models now. A couple of information about structure from motion. If you're processing these things in-house, they can require quite a bit of time, up to 48 hours or more to process, but new structure from motion software programs now are doing a lot of the processing in the cloud, and that's cutting the times down to 12 to 24 hours, and I'm hearing reports of even less in some instances. Different things that we can do with these point cloud models or with 2D orthorectified imagery is we can perform change detection analysis. So for instance, here's some images of a major landslide that occurred in the city of North Salt Lake in Utah in August of 2014. We were able to fly the landslide 2 hours after it occurred and create a 3D point cloud model from that, and that's shown in the image on the left. We were able to return to the same landslide several months later after some rain had occurred and fly the UAVs again and develop another point cloud model. And then using a 3D change detection like iterative closest point is a popular algorithm that's used, we're able to detect the average displacements or changes between the two models that give us an idea of how much movement occurred and where that movement also occurred. If we're interested in 2D, we can use registration algorithms like Cozy Core, and those have been around for a little bit longer than some of these 3D methods. Another potential useful application of the data is just to go in and use these models manually. So for instance, if I take that 3D point cloud model of the liquefied pier in Iquique, we can identify transverse lines across the pier, and if we were in the field and we had lots of time, we'd be able to run surveying measurements across and measure the cumulative crack widths of those ground cracks or lateral spread displacements. And what we wanted to do was perform a simple study to do that both manually in the field and then to take a student who had never been to the site and have that student perform the same measurement exercise but with the virtual model. And you can see on the right the comparisons between the measurements. The solid lines represent what we measured in the field while we were there, and then the dashed lines represent what the student measured from the virtual point cloud models. And you can see that we're really, really close to what we measured in the field. The value of this is that we can go back and we can perform measurements for these cumulative crack widths after the reconnaissance mission has been completed and after the field team has collected all the necessary data just to create these virtual models. In general, we were within about 9 centimeters of the final lateral spread displacements for the pier, which is quite remarkable. I'll turn the time over now to Dimitrios to talk about a few more applications that he's been working with.
Yes, beyond the imagery data that we discussed, I also mentioned the other sensors that are not as heavily used yet in geotechnical engineering, but I think we're going to see more of their use. I do want to mention that there is a lot of ongoing work in using geophysics within a UAV platform, and there was a special issue in the magazine of the Environmental Engineering Geophysical Society just a few months ago on the use of drones and geophysics, and many techniques, electromagnetic, hyperspectral imaging, magnetics, even seismic are being considered. And I think, in my opinion at least, UAVs have the potential to revolutionize these techniques and general non-contact sensing technologies, and not only as data acquisition, but also as computational platforms. Just recently, something that I think is we're going to see more in the near future. We've been playing with using drones for seismic geophysics. So these are some of the experiments in the lower part of the slide, where we're using a small drone to drop a small weight, and we generate a wave, a seismic wave that propagates and is picked up by the sensors. And very, very soon we'll be doing this at a larger scale. And what we can see is actually that we should be able to use drones for seismic geophysics, and potentially this technique could be a portable high energy input technique, much more higher energy than a sledgehammer. And so I think we're going to see more of that in the future, and it's going to be, I think, really exciting. The potential of that is that if there are areas, which many times there are after disaster, that you cannot really access, or maybe due to safety reasons you cannot approach them, a drone could potentially do this type of work instead of sending people. The next slide. Something else that I think is coming soon, very soon, because there are other disciplines working in that direction, is also that UAVs are, we have to recognize that they actually have powerful onboard processors. And so, although right now we do use them mostly for control of the drone and essentially data acquisition, the processing capabilities of these drones are huge, actually. And I think in the near future we can expect drones not only to collect the data, but potentially process it on board, use it to make decisions, and collect additional higher quality data. This is a picture, in the picture below that you see a satellite really photo from Nepal. In April there was a large earthquake in Nepal, April 2015, and you can see that there are some landslides over there. If Kevin clicks on the image again, potentially the drone could collect the data, but also use some detection algorithms and identify that it's looking at landslide or something that looks like a landslide, and make the decision to move closer and collect closer, higher definition data. I think we're going to see that much more coming in the near future, not too far distant future. The next slide. And finally, UAVs are already, I think, excellent data dissemination techniques. They can be used for disseminating data that they just collected. And the advantage of that is that if you can disseminate the data in an expedited manner, you can have remotely connected professionals and experts who will review the data and can provide feedback. We made an early step in that direction with the Lefkada 2015 earthquake, where, as I mentioned before, we were able to deploy within 2 days after the earthquake, collect the data, and it took us 2 days actually to upload it on YouTube. But because the drones had accessed a wide area that was not otherwise accessible, I mentioned before that the roads were completely closed. This footage was useful not only to professionals but to the broad public, and so it became very popular within a very short period of time. And I think the technology is there to make more steps in that direction and engage more people into the data that we're generating. Next slide. So in the next slides, in the next few slides, Kevin and I want to show some practical case history, some practical examples where what we're saying has been done, and hopefully that way communicate better the capabilities of the drones. The first case history is essentially a bridge scour failure in Greece, happened in early January this year. Essentially following significant precipitation and increase in the water level of a river near Kalambaka town. There was a bridge that was connecting and was crossing this river and was connecting Kalambaka town to some villages. And essentially one of the bridges, many actually, but one specifically was subjected to scour and moved. And as a result, the bridge pier toppled, and of course the bridge deck collapsed. We were able to go there again within 2 days after the failure, as soon as we heard about it. And obviously this area is not accessible. It's unsafe. And if you see at the right of the picture, you can see that the other bridge piers are also partially eroded and potentially under threat. And so we're able to fly the drone without approaching any closer while the river was flowing and map this structure using structure from motion. So what you see here in this image is a 3D point cloud of the model. It required about 649 photos from the UAV from different points of view to generate. It looks like a picture, but essentially for every single point that you see here, there's an X, Y, and Z coordinate, and you could potentially use it to collect measurements. You can see the location of the failure as well as the broader environment as well as the bridge. For the flight parameters that we executed, we have a point cloud density of about 0.5 centimeter, and we were able to do some surface surveying measurements, and we assessed that the model error was less actually than a centimeter, which I think is really, really, really impressive. In the next slide. In the next slide, what you can see is essentially once you have this model, you can do anything you want with it. You can cut a horizontal cross-section in the top left. You can remove the deck, the data points that are the 3D point cloud points that are related to the deck and look below. You can cut a vertical plane section and measure things. And so in this case, you can measure the horizontal and displacement of the pier that moved in the axis of the bridge and perpendicular to the axis of the bridge. You can measure the settlement of the pier, and you can measure rotations, obviously, rotation in the horizontal plane as well as the inclination of the pier. And this is, of course, information that you may use to calculate this failure or even look for ways to fix that failure. The next slide discusses a little bit another case history of a dam failure that happened maybe less than a month ago. And it's Parmos Dam, again in Greece. This is a 15-meter high earth dam that is used for irrigation. Although the media suggested that this dam was overtopped, the evidence clearly points out to that it was an underseepage and piping type of failure. The downstream side of the dam is heavily eroded, and there is clear evidence of piping, and at some section of it, essentially it washed away. And there was, of course, a water impounded in the back that rushed out and completely eroded the failure location. As the water in the reservoir dropped, there was a classic rapid drawdown failure, which you can see in the left side of the picture if you Kevin, if you can point in the lower figure, the left failure is a rapid drawdown failure that the locals actually saw it. They saw even the elevation of the water when it actually occurred. We were there again today immediately after the failure, and it took us about 4 hours to map the dam as well as the flood below it, and I'm going to describe that in the next slide. Again, structure from ocean is used, and what you see at the top right figure is a 3D point cloud of the failure with tremendous, I think, detail. Some of it we want, some of it may not be directly useful, but it is a significant amount of data that is generated out of this process. And once you have a 3D point cloud like that, you can cut a cross-section. So in this presentation, just cut a cross-section through the rapid drawdown failure, and you can see the cross-section of the failure before and after of the failure location before and after the failure. And this, of course, will be really valuable if we were to calculate this type of failure. If we go to the next slide, what you see in the right figure, at the top right of the figure, is a dam. We have been focusing on the reservoir and the dam itself. Reportedly, a 5-meter wave was generated out of the abrupt emptying of the reservoir that eroded all the way down 1 kilometer. And you can see the flow of water all the way down until it found a natural stream where essentially it stopped there. And this is so I'm showing this example because it covers significant area of about 1 kilometer in length and maybe 300 meters in width. To create a model like that, and in order to have reliable data, you do need to ground truth your model. And so we use RTK GPS. For this model, we used we collected 18 GPS points. 12 of them were used to scale the model and make sure that the model dimensioning is correct. And with 6 of them, we were able we use them to assess how accurate is our model. And so we calculated that the model has a mean error of about plus or minus 2.5 centimeters from what we saw, which I think for an area of that size is really, really good. Again, it depends on the objective, of course. If Kevin clicks in a little bit more, what you can see is the flow. You can upload that to a GIS platform, and what you can see is the flow of the water, the impacted area. Keep clicking, Kevin. Of course, you can calculate the flooded area. You can calculate the volume of water that is essentially was released. If you know what was the elevation at the time of release, you have the 3D model, so that is really easy. And of course, along the way, if there are certain features that you want to focus on, you can look at that. For example, there is a picture of a structure that was downstream that, of course, got overwhelmed by the flood, and you can use that to information. So what I'm hoping to communicate with all these discussions, it's already pretty obvious that once you have a model, you can do all of that stuff, is that the amount of data that you generate in 4 hours, at least field work, significant analysis to be done, but in 4 hours of field work can be tremendously significant. And I think it is it is really a very competitive technique to collect very valuable data that we couldn't do it before otherwise, at least not with that level of effort. The next case history is also, again, I was trying to focus on larger features. This is a monsoon-induced debris flow. And as I mentioned before, in April 2015, there was a major earthquake in Nepal that caused significant landsliding. The debris from a number of landslides in one of the canyons in Nepal was essentially the source material for a debris flow that was during the following monsoon was mobilized, and what you see here is a model of the deposition area of the debris flow where it stopped essentially. And again, there is a digital terrain model to the left, and once you have that, you can create contours, measure elevations. But what I think is also exciting from a geotechnical perspective, and we're still not taking full advantage of that, is that you do have a high-quality imagery. And so if Kevin clicks a couple of times, what you see is very significant, as this debris flow was losing energy, it was depositing first the coarser grains upstream, and then further downstream was had less energy and was carrying only finer grains. And you could potentially use this information to even calculate. I know it's a stretch yet, but we have the data to maybe even make some analysis of the dynamics of the debris flow from this technique. And the next case history is related to infrastructure. This is just a relatively small port pier in the port of Vasiliki that was damaged during the magnitude 6.4 Lefkada earthquake. It's just 12 meters wide and 73 meters long. It took 7 minutes of flight time. That was flight time, not length. So very short period of time, flew relatively close, and as a result you have a very good resolution, less than a centimeter ground sampling distance. And an output of that is essentially an orthophoto and a 3D point cloud, of course, but an orthophoto that you can actually use to measure any type of width of the crack that you want, and that is shown there. But I think what we will see in the future is not just manual dimensioning of the cracks like we're doing here, but if Kevin clicks one more time, we can use automatic identification feature recognition techniques. And this is a routine that was implemented by my colleague, Professor Jahan Shahi from Purdue University. He has developed that routine, and I gave him the 3D point cloud, and he applied his routine and was able to identify automatically all the cracks. And I'm not showing that here, but it was also able to tell us for every single place, automatically calculate the width of these cracks, which I think is really, really powerful if you think, because all of you that have done this work, you know we have to go manually measure all these cracks. That can be tremendously time-consuming. And with techniques like that, we may be able to not do this in the future and save this time for something else. The next case history, this is a reference of Dr. Jahan Shahi's work. A question, this case history, I added it here so that I can answer a very common question about the reliability of these 3D point clouds. So, okay, we get a 3D point cloud. Is it correct? The answer is yes. It is a very reliable 3D point cloud if you do this correctly. And this has been shown for different applications by different disciplines. I have here a geotechnical one. These are a set of coseismic landslides in Nepal. They are 200 meters in height. And what we did is fly the drone and perform structure from motion and to create a 3D point cloud. And my colleague, Dr. Kristen Cook from Potsdam University, had a ground-based LiDAR that she used and created also a 3D point cloud. And we were able to, of the same target, and we were able to compare the two 3D point clouds, and they were practically identical. At the lower right of the slide, you can see essentially the 3D point cloud. And at the top right of this slide, there is a cross-section, just one of them, cross-section number 5, of a cross-section through the 3D point cloud. And with the pink, you can see the structure from motion, drone-based 3D point cloud. And with the green is the LiDAR 3D point cloud. And I hope you agree with me that for all practical purposes, these 3D point clouds are identical, which is very exciting. The next case history is a little bit taking this a step further. Up to now, we've been focusing and describing to a large degree observations associated with geometry. However, with advances in image analysis, this may not have to be the case. And so what I'm showing here is an example for some rock slope slides in Nepal. And in the top left figure, you see a 3D point cloud with a debris cone highlighted. We can cut a cross-section through that point cloud, and you can get the geometry of the cross-section, but identify visually the residual soil, and the rock, and as well as the debris cone. And then if you zoom in, because you do have high definition imagery, you can zoom in and really see very closely the rock structure. And this happened to be a broken knap formation, significantly fractured, a classic hook and brown material. And if you have used that technique, we use the geological strength index for that, which is essentially a visually based parameter that is indicative of the structure of the rock mass and its weathering state. And you can get that information from the drone. And so you can assign essentially GSI values based on the observations and essentially create the strength of that rock mass. And so at the end, you don't only have the geometry, but you have the material properties too. And of course, if you have structurally controlled failures, what happens in many rock masses, then you can measure the attitudes of the discontinuities and collect that data too. Notice that this is a 70-meter high rock slide, and we were sitting at the toe of that. We were really, from the ground, we could never have seen anything on the backscarp of this landslide. We were practically looking only at the debris cone, and with the drone we were able to get close to it and see the rock mass and characterize it. And so I think there are tremendous opportunities in that direction. And the next slide, I think Kevin has also some additional examples that are really exciting to show you.
I do. Thank you, Dimitrios. That's really good stuff. And so the next few case histories that I want to share with you are some of the work that we've done. And essentially, I just want to show some of the animations of the models that we've developed. And with the great information that you saw from Dimitrios there, we'd be able to apply those techniques to these types of models to learn and understand a little bit more about the processes and mechanisms that cause these failures to occur. So I'm going to apologize beforehand because when I try to run these animations, though they'll look great on my computer, I know that as we are streaming this over the internet, it may look a little blocky or clunky to you. But down below, you'll see the web address to a YouTube site where you can view these videos in all their resolution and glory. And so feel free on your time to go and check these out if you'd like. The first case history that I want to share is, again, that North Salt Lake landslide that occurred just a few miles north of Salt Lake City, Utah, in an upscale residential part of the town. We were called 2 hours after the landslide occurred, and we mobilized immediately. And so we were able to fly the landslide in a relatively short amount of time. I think we collected all the data and imagery we needed to create the model that you now see in less than 2 hours of time. And we needed that short amount of time because another rainstorm was approaching that afternoon, and so we couldn't spend a lot of time on the site. But as this animation zooms out here, you're going to see just how scary this was. This, you can see that there was a home on top that was impacted. You can also see that, or maybe you saw earlier that down below there was a house that was hit by the debris from this landslide and completely collapsed. Fortunately, the family was able to escape minutes before their house collapsed around them, and so there were no fatalities from this event. But it really is quite a remarkable landslide. And we got a call again from the Geological Survey and asked us to go back out last week because their sensors were detecting some movement starting again. So we were able to go out and fly it, and we're in the process of creating another model of the landslide. Since that time that we flew it, the Geological Survey is telling us the landslide has moved over 5 inches and continues to go again. And this is after engineers have attempted to stabilize the landslide. So this should be interesting to continue to watch. The next is another landslide that occurred in Arizona. south of the city of Page in 2014, and this landslide was kind of a social media phenomenon because this is a popular route between Lake Powell and Phoenix, Arizona. This landslide cut across a well-used highway, Highway 89, and completely ruptured it. So you can imagine the landslide was closed. We were able to fly the landslide about 5 months after it occurred. That's how long it took us to get our authorizations in place. But it was a very large landslide, over 500 meters in length at the toe. And the landslide caused the highway to be closed for approximately 3 years. Just as last summer, they completed the remedial efforts for this landslide, and now the highway's back up and running again, but we were able to return to the site and create another model of the repaired landslide, which we think is kind of interesting to look at the before and after. But again, one thing that Dimitrios mentioned earlier that I'd like to point out, you can see zones of shadow across the road, and this was because we were flying very early in the morning before it got to 120 degrees air temperature. And once it got above about 100 degrees, our UAV started having malfunction problems. So you can see the impact, the shadows on the road. We were still able to create point cloud models, but the points are obviously discolored because of the shadows. The final case history I'd like to share with you is a rock outcrop in central Utah. It's pretty famous with geologists. It's called the Book Cliffs, and specifically we're in a location called the Son of Blaze Canyon. And we were asked to go in and model about a kilometer-long section of this canyon. The thing that's remarkable about this model that you're seeing now is that it's about 1 kilometer long, but the depth of the canyon is over a kilometer deep. And we're on the other side of the canyon more than a kilometer away, and so we're flying our UAVs with what's called first-person view, or it allows our pilot to be able to see what the UAV is seeing, even though we can't physically see the UAV itself. And so that's kind of a scary experience, but we were able to collect this great resolution imagery of the canyon. And the beautiful thing that at least those who were funding our research with this was they were interested in testing the ability to detect rock layers of interest. For instance, if for a post-disaster application, if we know that there are particular geologic layers that are prone to strain and to failure, we might be able to identify those from these high-resolution 3D point cloud models. So we're going to move to the final topic. We're coming to the close of our allotted time here. We want to talk a little bit about a few of the lessons learned from the field, so hopefully you can learn from our mistakes and not repeat them. A couple of things when we talk about major considerations. We want to talk about, first of all, the topic of UAVs and their sensors are explosively changing and growing. And just when you think you have your arms wrapped around it, it continues to advance and to improve. And so it's really exciting to be a part of and to watch. We're also seeing regulations are evolving, which are really important and will allow us to be able to fly in places that otherwise we may not be able to fly. We want to emphasize the importance of safety. UAVs can indeed cause injuries or even death. And so it's important that whoever's operating UAVs need to be sure that they're following a proper safety protocols and following the local laws. And if you're flying a UAV, it does require a lot of practice. There tends to be this idea that you can go out and just open the box and fly a UAV and get good data. We found that when you try to do that, oftentimes you're going to crash your platform. And so it does take practice to learn how to do it without crashing and to get the kind of data that you want. But once you have an experienced pilot, you can get a lot of excellent data. And so in order to acquire this good quality field data, it's going to require even more practice, more experience, and the appropriate type of equipment. You need to consider the type of drone that you're using. You need to consider how you're flying it. How far away are you from the target? What's your elevation? What's your point of view of the object you're trying to see? And you need to maneuver that UAV to get the best point of view. You need to consider that the sensors that you're using and the characteristics of the camera and make sure that you're using the right sensor with the right type of data you're trying to collect. All of these things are going to ultimately impact the quality of your data. And if you fail to consider one of these important aspects, the quality of your data is going to be negatively impacted. And we'd like to point out as well that every single flight should have a specific objective. Sometimes it's tempting to just get out there and throw your platform up in the air and say, let's see what we can get. We find that you're not very efficient that way. You should know before you put your platform in the air exactly what it is you want to see and what it is that the type of data you're trying to collect. If you want to get quantitative measurements from the UAV data, we strongly recommend the use of land-based ground control points with GPS or other similar surveying equipment because they can correct your model, improve the accuracy, and ultimately improve the measurements that you're going to be making from that model. I want to also focus on the importance of considering the environment that you're flying in as well as the weather conditions. It's very important to match the UAV and the pilot to the environment and the weather. Many of the UAVs that we've flown are very sensitive to wind, which means when you get a wind gust above about 20 miles per hour, it can knock them out of the sky. And so you need to be careful with that. Some UAVs, like we saw in Arizona, can also be sensitive to temperature. Others don't seem to be bothered by it. So it really behooves you to do your homework before you take a certain UAV platform out in a particular environment. One thing that we have noticed when you're in difficult environments where you might have temperature problems or you might have extreme wind, we've noticed that the single rotor platforms perform really well. We've flown our single rotor helicopter in wind gusts of 50, 55 miles per hour, and it has had no problems at all. And again, we believe that's due to the large polar moment of inertia of that single blade that's spinning. But if you're not careful with these things, you could have the same thing happen to you that happened to us. For instance, we tried to fly a large rock fall near Salt Lake City with this small little UAV. Unfortunately, that day there happened to be a winter storm up in the mountains. Where we were standing watching it, it was fine. But you have to consider where the UAV is flying, not where you're standing. And the wind gust pushed the UAV back behind a large boulder, and we lost radio connection with it, which initiated the automatic landing sequence for the UAV. Unfortunately, it tried to land itself on the side of this rock fall and crashed and ended up getting buried under 6 feet of snow for nearly 5 months. And this, of course, after 5 months when we hiked back up and found it, this is what we were able to retrieve. I'll use this moment to give a hearty thumbs up to GoPro cameras. Even though this GoPro camera here was buried under the snow for 5 months, it still worked perfectly fine, and we were able to retrieve all the imagery from the UAV before it crashed. I want to talk a little bit about hardware and software as all. I want to note that good drones don't need to be expensive, particularly if you have skills or plan to manually upgrade a hobby or a toy aircraft. However, if you go and purchase a commercial UAV, be ready to spend some money in a lot of cases. A lot of commercial platforms like DJI platforms are very affordable and you can purchase for less than $5,000. But others can be a lot more specialized, like the SenseFly, the Trimble. Those types of platforms can be in excess of $40,000, especially if they have a lot of specialized or automated features. I want to point out, it's been our experience that large UAVs tend to require lots of maintenance to keep them running well, and it helps if you have an experienced personnel or technician oversee that. The small platforms, like the little DJI quad rotors, tend to require minimal maintenance, and they're very reliable, but the type of data we can collect from them tends to be limited because they can't carry a very large sensor. Batteries tend to be the governing issue in operating UAVs in the field. We recommend you have multiple sets of batteries on hand and that you have a means to charge them in the field. If you're flying a lot, we recommend you replace batteries at least annually, and otherwise the batteries can just die without notice. That happened to us once. We had a platform 200 feet in the air, the batteries just died, and the platform crashed, and we lost both the sensor and the platform. Lots of times we focus solely on the platform, but we don't give a lot of attention to the gimbal that the sensors are mounted to. In my experience, the gimbals are the trickiest part of the platform. The sensors can be heavy, it can cause problems with the gimbals. So make sure if you're going to spend money on good equipment that you probably want to spend that on getting a reliable gimbal for your sensor. In terms of structure from motion software, which we've shared a lot of images and examples for, there's a lot of options out there, and I mean a ton. And so we've experimented with many. Some are better than others for certain things, but in general, for the quality of the models, we've noticed that they all produce pretty similar models. If you want to operate structure from motion in-house at your own institution, it's best to have a workstation computer. It's difficult to perform this from a small desktop or a laptop computer. It can take a lot of time. Typically, the cost for a workstation computer is going to range between $5,000 to over $20,000, depending on how many bells and whistles that you put into it and the configuration. The thing that makes these workstation computers expensive is the graphics memory and the graphics cards. These workstation computers need lots of graphics capabilities to do this work. Fortunately, a lot of structure from motion, though, is moving into the cloud. And we've seen a lot of potential promise for that, and we think that that trend will continue, and we're excited about it. The one downside to this is that it limits our ability to control the 3D reconstruction and to be able to scale things, mask out certain parts of the processing that we don't necessarily want to have processed. But I think those capabilities will come with time as well. I want to talk a little bit about the realities of UAV automation. And I think everybody's probably seen videos like this on YouTube where, people have trained or taught their UAVs to do all sorts of crazy things. Crazy things like go play in a symphony, or to take a box of beer and to deliver it to somebody who's ice fishing. And because of these types of videos that are out there, I think it leads to people to believe in our society that drones are a lot more capable in terms of automation than they really are. What we need to understand is that when we see videos like this of a drone delivering some beer out to folks who are ice fishing, what we need to realize is that these drones that you're seeing really have been trained to do a specific thing very, very well. But if you try to get them to do something else in an automated fashion, they're going to fail miserably. The reality of UAVs and robotics is that these experts working on these areas are still struggling to solve basic stuff, like the problem was called perch and stare, or to use vision-based information to automatically navigate the UAV and to change its decisions of where it needs to go. So if you're planning to spend a lot of extra money to get a UAV that claims it has a lot of automated capability, you may want to just stop and think a little bit about what you're really getting for your money. Most current automated algorithms will only allow the GPS to fly at a pre-programmed altitude, and it's going to fly in a pre-programmed flight pattern based off GPS. If you're flying in an area where GPS signal doesn't exist, whether it's a cluttered urban terrain or whether, for whatever reason, there may not be satellites in the sky, those automated functions are not going to work. Another thing to consider as well is that automated takeoff and landing generally works well when you have GPS signal. If you don't have GPS signal, then you better have a backup plan because your platform is probably going to crash itself. In terms of windy weather and automated flight, if you have wind and you have pre-programmed flight paths, expect a significant increase in your battery drain. Your flight times may be diminished 30, 40, even 50% because of that wind. So with that, that's all of the material that Dimitrios and I have prepared and wanted to present to you. We've gone a little bit over time, but at this time, we'd like to encourage you to unmute your phones, and we'd be willing to take 5 to 10 minutes worth of questions if you have them. If you have questions and aren't able to fit into that time frame, feel free to email me or to email my colleague Dimitrios, and we'll be happy to address those individually as they come to us. So Dimitrios, is there anything else you'd like to add before we answer any questions?
No, I'm good. I'll be glad to answer any questions there are.
Okay. Well, excellent. So with that, if you'd like to ask a question, feel free to unmute your phone and ask away. Anybody with questions?
No questions, looks like, again.
Okay. Well, we appreciate then your participation. And if you have any questions come up afterwards, again, feel free to email us. But with that, we'll go ahead and end this webinar. Again, this has been recorded. Oh, yeah, go ahead.
Yeah, I was wondering, for the software that processes the images, is that typically a private software that would be purchased from different companies, or are there also publicly available softwares?
Dimitrios, you want to take that?
Yes, so you know, I definitely would like not to advertise specific software, so that's why I'll avoid saying names. But there are a large number of softwares that are commercially available, and there are some open source ones that are. The open source ones tend to be less, well, actually not less powerful, but less user friendly. Obviously, require more work, but they are. You can do almost anything you want with them. While the commercial ones, you know, you have to follow what the options are, and you are a bit more restricted. And there are even in MATLAB you can find some software for manipulating some of these 3D point clouds, but it's more work. If you want, we can definitely provide. You know, if you actually put structure from motion software, you'll find lots of names. But if you have any trouble with any of those, I'll be glad to by email to respond to that question for sure.
All right, and my last question would be if we wanted to know a little bit more on how exactly to go with the process of, you know, from getting it drawn, taking some imagery, and then interpreting the data, is there a good starting point in terms of bibliography, a journal, a book, anything that you would recommend as a starting point to get involved in this?
Kevin, you want to take that, or I'll do that one, so whatever you want.
Well, no, that's fine. So structure from motion has been around really since the 1970s, and there's extensive literature that describes it. If what you're looking for or seeking is a resource or a reference that teaches some of the basics behind structure from motion, my recommendation would be to find a reputable computer vision textbook, and it's certain to have a chapter or a section in there that will talk about structure from motion. If you turn to the journal literature, you're more likely to find more sophisticated and advanced techniques that are related to structure from motion or advancing it, but they may be very difficult to understand. Dimitrios, would you add or say anything different to that?
No, I will say that, the principles behind it is really photogrammetry, practically, but now implemented, of course, within a digital framework that you have to much more data, essentially, to process to do this work, and that's why we use that type of software. But, yeah, basically, I think also if you buy, or as you're considering different types of softwares, they do have commercial softwares, if you decide to go that route, they do have some manuals that along the way they help you. You can get some of the background that way.
Yeah, that's a great point. We enjoy reading the technical background from the software that we use, and it's very easy to understand and explains a lot of what's going on.
All right. Thank you very much.
Thank you. Are there any other questions that you would like to ask?
I have two questions.
Okay.
The first one is to make a 3D point cloud database, do you need to capture all the images in the one flight, or can you make a few different flights?
So that's a very good question. The assumption that structure from motion makes when it creates a model is that the environment that you are imaging is static and not moving. Anything that moves, if you try to process that as one model, it will be removed from the processing. And so if whatever it is that you're imaging has changed in any way from time A to time B, then your model is not going to be good quality. And so it's best if you just collect all of the imagery from one time so that your model represents essentially a snapshot in time. And then if you want to return and collect imagery at another time, then you can create a model for that other time and do a change detection analysis. But, for instance, there have been studies and a lot of research done where people would take, say, imagery from the internet of famous landmarks or structures like the Sydney Opera House, and you could imagine those pictures were taken by different cameras, by different people at different times, and they still show that you can take those images and create a model of the Sydney Opera House, even though those images came from different cameras and at different times. The thing, however, that makes it work is the assumption, again, that the Sydney Opera House did not change at all, and that it's the exact same structure in all of those different times.
Okay, then my other question is, for example, you guys actually made a very nice images from the landslide areas, but to qualitative enough like landslide images, and I understand that there are many variabilities over here, but from one flight, how large area you can actually cover?
I think, Dimitrios, you're probably better to answer this because you've analyzed some pretty large areas.
Yes, so I think these are among the decisions that you have to make at the end. If you have it, or not if, you're going to have a specific camera that has a specific resolution, and for that specific camera, if you fly very close, you'll get high definition data. If you fly far, you're not going to get as much. And so many times when people ask me something like that, I will say, okay, what are you trying to get? Because if you're trying to get a 1 centimeter wide crack and you fly 300 meters above, you may not be able to see it. And so many times, personally, depending on the feature, of course, I will have a broad flying to get a broad DEM of the entire area with some specific error. And then if I know that I'm targeting a specific feature, I will fly closer in a specific pattern to get this in more resolution. And that will require, in that case, a number of flights. It's a function of what your battery life is. Some of these quadrotors have 20-minute or so flight time, and so you may have to land and come back to do this. This is also the difference between the fixed wing and the quadrotors, that their quadrotors can actually stay in one place and zoom in more and go up and down, while this is much more difficult, possible actually, for fixed wing. And so again, that's where we're talking about the type of drone that you have also will affect the type of data you can collect. So I mean, if you were to consider to buy a drone and look into that, the first thing I would look is what camera does it have, and can I mount a different camera? I mean, there are some people that are mounting cameras on drones that are far more expensive than the drones themselves.
Okay, thank you very much. That answers my question.
Great.
Okay, well, if anyone has any remaining questions, feel free to email them to us. Our contact information you can find online. We'll go ahead and end this webinar. Thank you for your participation. Again, if you want to rewatch any portion of this, the recorded webinar should be available on the GEAR website within a couple of days. With that, Dimitrios, thank you for your participation. The work you're doing is fabulous, and this has been a great opportunity to collaborate with you.
Yes, it's been a pleasure, Kevin, and thank you everybody for your interest in this. Bye.
Goodbye.